Okay, so again, high-level overview, what you need to know, the different types of petroleum, the reservoir recovery mechanisms and how they affect recovery estimates, estimation methods, natural gas, we'll talk a little bit about shrinkage, sales gas volumes, and byproducts. So the purpose of reserve estimation, we talked about the income method in valuing assets. So reserves are essentially the primary input in oil and gas asset value. We need to forecast future cash flow, and that starts with production. You multiply the production by the price to get the gross revenue. So we're really focusing for the rest of the day, we're going to be focusing on this production piece. We're going to be focusing on total recoverable volumes and how you estimate how and how long it will take to produce them. So going back to the definition of petroleum, crude oil, bitumen, natural gas, and related byproducts like NGLs and sulfur. Alright, so what are reserves? We spent a lot of time talking about them already. So for regulatory reporting, estimated volumes of petroleum that will be recovered commercially from known accumulations. We've seen that exact definition a number of times now. In practical work speak, so in layman's terms, estimated volumes of petroleum that will ultimately be recovered. Formal meetings are for a select group of people and very specific purposes. Again, what we're looking at, just a wide variety of projects. Recoverable volumes. We're looking for recoverable volumes of light, medium, and heavy crude oil, bitumen, natural gas, NGLs, sulfur. So getting a little bit into petroleum and the various from light to heavy molecules of petroleum. So you can see methane, so CH4, natural gas, ethane, propane, butane, and most of the remainder are what we call NGL byproducts. When you get into the really heavy stuff, that's when you're getting into the oils. Two concepts with oil, you have density and viscosity. So when we talked about API gravity earlier, that's a measure of the oil's density. Viscosity is the ability of the oil to flow. Viscosity can cause major issues in extraction processes. So it's the reason that bitumen does not flow until you heat it up. So you can see they have a correlation here between viscosity and API gravity. It is also temperature dependent. So just an interesting plot to just give you an idea of how thick oil can really be. So these are the Canadian major bitumen deposits, and on the left side you can sort of see it. You got temperature on the x-axis, and you can see as you heat up the oil, the viscosity, which is in red, starts to drop. So bitumen starts thicker than peanut butter. It's very thick. If you had it in a cup at many reservoir conditions and you turned it over, it wouldn't move. Eventually, when you heat it up to 150, 200 degrees with steam, you have very mobile oil. A little note on the bottom says SEG-D took about 20 years to get field operations. So SEG-D started as an academic exercise. It started in the universities in Canada. It was a long process to get it from theory to practical application, and now it is one of the largest driving factors in the biggest reservoirs in Canada. So types of crude oil, these definitions fall in line with how the regulator defines, so this goes back to disclosing types of crude oil. COGI also has definitions for which buckets crude oil falls into depending on its physical properties. So light oil, API greater than about 30 degrees. In terms of producing light oil, unassisted flow in the early life, pump jacks or submersible pumps, and EOR floods in the late life. Medium oil, same production methods as light, so medium is very similar to light oil in terms of how easy it is to flow. APIs between 20 and 30. Heavy oil, APIs between 10 and 22. Again, heavy oil doesn't necessarily require thermal production methods or solvent production methods. Some heavy oil flows by itself. Again, it's dependent on that API. Field processing, so concept of an oil battery. So these
with our thousands and thousands of oil wells in Alberta, one of the most common field infrastructure that you'll see is oil batteries. And the purpose of an oil battery is simply to separate formation water, solids, and gas from the oil so that you get separate streams coming out of the field. So these essentially consist of a giant tank, and they allow the mixed product stream. So almost all production that comes out of the wellhead is going to have some component of formation water with it. It's going to have some amount of gas due to the pressure dropping as it comes up to surface. And a lot of times there's going to be solids like sand coming up with the production. So what they do is they flow the oil from the wellhead into a giant tank, and they essentially let it settle. The gas rises to the top and can be vented out the top and either flared or conserved and sold. The oil is sort of the middle layer. It sits in the middle, and you can skim it off the water. So the water sits below the oil and can basically be produced out the bottom and disposed of or re-injected. And the sands will settle down to the bottom, and the sands get pulled out. And there's a number of applications for the sands that come out. They use it for sanding roads, etc. Upgrading plans for oil and bitumen. When you're producing bitumen, because you have to heat it up, you have to steam it to get it to flow, you bring it to surface, and then if you allow it to cool down, you're going to have real issues. So they do when I talked about transporting products by rail, they can put bitumen in rail cars. It solidifies to essentially a crayon type consistency, so it's basically a solid, and they can rail it to various refineries or markets. But if they don't do that, they usually have to get the oil up to pipeline specs so that it flows within pipelines, so they will blend it with condensate. They'll blend it with a light end so that the mixture of oil flows at normal conditions and meets pipeline spec. We also have upgraders for upgrading bitumen to what they call synthetic crude oil. So that's just you're applying heat and pressure, and you're cracking the very large oil molecules in order to create smaller ends that flow more freely. Moving into natural gas, so there's three major types that are identified in oil and gas disclosures and evaluations. You got solution gas, which is gas that's dissolved within crude oil at reservoir conditions. In terms of estimating future solution gas, it's generally estimated as a gas-oil ratio. Gas-oil ratios for most solution gas-driven reservoirs stay fairly constant over time, so it's pretty simple to just apply a gas-oil ratio to the oil production to estimate the gas reserves that you'll get out of the reservoir. Non-associated gas is gas that's not in physical contact with oil, so this is a separate accumulation that only has gas or gas and water. There's no oil in the reservoir, it's simply just a gas reservoir. Estimation methods, analogies, volumetric calculations, performance methods, so we're going to be talking a lot about those today. And then associated gas, which is you're looking at gas caps, you're looking at gas that's you have a reservoir that's a mixture of oil and gas. And the evaluation methods or estimation methods are the same as the non-associated. Okay, so what is natural gas? It's a mixture of naturally occurring gases. It's mostly methane. We'll look a little bit at the compositions in just a few slides here. Mostly CH4. So here you go. Composition range. Methane ranges from 50 to 95%. It's usually in the 70 to 90% range, methane. And then you look at all the byproducts that make up. So these would all be in a gaseous phase. They would all be in a gas stream. So the ones we deal with the most for NGL byproducts are ethane, which is a very light end. It has limited uses in North America. It's highly there's a lot of use for it in countries like the UK. So different markets have different needs for different products. Propane, butane, pentane. So the first three, ethane, propane, and butane, C2, C3, C4, those are modest products in North America. They add value to gas, but they're not. They're generally not a large portion of the value pie. All the rest of these generally get lumped into what we call pentanes plus. So pentane, hexane, heptane, anything higher than C5 generally gets lumped together because their percentages are so low once you get beyond pentane. And that's where a lot of the value is created in Alberta. Pentane plus is what's required to blend with bitumen. It's sort of synonymous with condensate. So there's a large market for pentanes in North America. And then you look at the non-hydrocarbons. So these are things that are basically just taking up space and they don't add heating value. So they're not adding value to your gas. You got nitrogen, CO2, H2S. So CO2 and H2S are what make up what we call acid gas. So they're difficult products to deal with. H2S is highly poisonous. So when we have sour reservoirs, we have to have very strict conditions in place for how to produce H2S and how to deal with H2S if you have leaks or issues. And then you've got a few other small products, Captain and helium. So looking at all the terms you might see with gas, so natural gas, that's what you hear a lot. It's the full mixture. Raw gas is the gas you get at the wellhead. Raw gas is the total gas coming out of the ground. Sales gas is the processed natural gas. So processing might be as simple as collecting what's basically methane from shallow gas wells and simply putting it, as long as it meets pipeline spec, putting it in a pipeline. So it might be as simple as separating water from gas and putting it into a pipeline. It could be as complex as running it through a deep cut facility and recovering most of the byproducts in the production stream. So now you have concepts: dry gas, wet gas, and rich gas. So I've talked about this a little bit. Dry gas has, in terms of C2, C3, C4, C5 plus, it has relatively low compositions. So dry gases are the ones that are going to be 90-95% methane. Wet gas is gas that produces condensate. So condensate is those pentanes plus, but it's called condensate because it's not entrained in the gas. It's actually a separate product that comes out of the reservoir. So condensate is synonymous with a very light oil that comes out with gas production. So it's usually APIs of 40 plus, sometimes upwards towards 50. So it's very, very light oil. Rich gas is gas with high NGL content. So that means it has a lot of C2, C3, C4, and C5 plus entrained within the gas. Liquefied natural gas, or LNG, very large industries in Australia, the US is starting to get in on it. This is how they transport very large volumes of gas to overseas markets. Natural gas liquids, again, ethane, propane, butane, pentanes plus, and you'll hear me call them by those names or by C2, C3, C4, and C5 plus. Compressed natural gas can be used as fuel. There are vehicles in Canada. Some of the oil and gas companies actually run vehicles on compressed natural gas. And liquefied petroleum gas is similar to LNG, but it's mostly, it's not methane that they're compressing, it's mostly propane and butane, also used for fuels. High-level overview of gas processing. So you bring the gas out of the reservoir. This is usually what's called a free water knockout. That's where you're separating formation water from the gas. The gas then comes through. You may have a dehydrator, which is basically, you have free water that comes out of the formation, and then you also have water that is entrained in the gas, so sometimes you have to heat up the gas to dehydrate it. Sweetening is when I said acid gas for CO2, for carbon dioxide and H2S. In order, you either have sweet gas or sour gas. So acid gas is also called sour gas. So the process of removing carbon dioxide or hydrogen sulfide is called sweetening. removing NGLs, so that's usually, you'll run the gas through refrigeration, you'll drop the temperature or you'll drop the pressure significantly and drop out the liquids phases and recover those byproducts. And in pretty much all gas streams that go through processing facilities, you'll have compression to make sure that the gas is meeting inlet pressure requirements and outlet pressure requirements for going into sales lines. So here's some real world examples of gas compositions in Alberta pools. Not going to spend too much time on this. You can see the methane percentages. So Suffield Medicine Hat is very shallow gas. This would be similar to CBM in Canada, 96% methane, so it's very dry gas. We got two different Montney pools, and you can see at the bottom, it's showing you that these wells, the gas compositions from these two wells are very close, so gas composition can change significantly over short distances. So 6 kilometers away from one another, you have gas that's 94% methane versus gas that's 6 or 7% lower, which means it has a lot more heavy ends in it. Kaybob Duvernay, just a different play, very rich in liquids, so you can see it's only 70% methane. And then Caroline Beaver Hill Lake A, the other thing to look at on these is the H2S content. So shallow gas is almost always sweet gas. If it wasn't sweet gas, the other component with sour gas is that it's very expensive to deal with because H2S is such a heavily controlled substance. So shallow gas, virtually always sweet. Montney gas, you can get sour Montney gas. But when you look at, they're putting Beaver Hill Lake A, it's a deep reservoir, very, very sour. 33, 35%, 30+% hydrogen sulfide, that's a big deal. Hydrogen sulfide can kill a person in seconds if the percentage is higher than 0.5% or 1%. So in Canada, because we do have a lot of sour formations, we have a lot of H2S training within the industry, and everyone is well aware of the dangers of H2S. So getting into methods of estimation, we talk about primary, secondary, and tertiary recovery mechanisms. So primary recovery uses the natural energy of the reservoir. So you're drilling a well and you're allowing the reservoir to produce the fluids on its own. Mechanisms for that: oil, you may have solution gas or gas cap expansion, or gravity or water influx. So usually what's providing the energy to an oil system is either the entrained gas or water that may be either pushing up from the bottom as an aquifer or encroaching from the sides. So the gas and the water are what we call drive mechanisms. Secondary recovery, this is really talking about water flooding and chemical flooding. This is injecting another substance into the reservoir to sweep the reservoir and push additional recovery towards the other wellbores. And tertiary recovery is getting into the more complex mechanisms, such as CO2 or miscible flooding, where they're injecting miscible gases to lighten the oil in the reservoir. And thermal processes like SEG-D, steam recovery. So what methods do we actually use to evaluate? There's 3 major categories that we distinguish. Volumetric methods, which is really looking at the total volumes within the reservoirs, within the rocks. Analog or performance prediction methods. So this is when you have a little bit of data in your reservoir and you have a lot of data in other reservoirs around it, so that you can apply the performance you're seeing in a separate accumulation to your subject reservoir. And finally, when you have a lot of data in your reservoir, you move to performance methods, where you're interpreting trends to estimate recovery. And performance can be broken down into a number of different types of methods. We'll talk about all of them: decline curve analysis, material balance, computer simulation. It references a very famous paper in oil and gas called ARPS. ARPS was one of the first people to describe decline analysis and the relationship between rates, pressure, and fluid flow. So when do we use these various methods? It depends. It depends on how much data you have. It depends on what type of asset you're looking at, and it depends on how the resources you want to allocate to the estimation. Some methods are very simple, very quick. Some methods take days, weeks, months. So analog and volumetric methods are used for immature, early stage development when you don't have a lot of data. Performance methods are used when you have a lot of data. And any evaluation is going to include a mixture. You will very rarely see an evaluation where everything is done by performance methods or everything's done by volumetrics, because you always have individual assets in different stages of development within a portfolio for a company. Accuracy. Some methods are easier than others, but all methods, the accuracy is going to depend on the validity of the data, the volume of the data, so how much information you have, the skill of the evaluator and the bias of the evaluator. As a general trend, as you get more data, your volumes are going to get more accurate. And we've talked a lot about how the 1P and 3P start to converge on the best estimate as you get more data. That's really what this is talking about. It mentions Alberta specifically because we have a world-class system for recording and reporting oil and gas information. So we're one of the better jurisdictions in the world for requiring companies to disclose large amounts of information on their oil and gas assets, and it's all publicly available. So getting into unconventional and resource plays, we use the same general techniques as conventional plays, but you have to be careful in applying them. You have to know what you're doing. You have to understand the differences in production profiles and recoveries, which are really driven by reservoir mechanics and fluid dynamics. In unconventional assets, the initial declines are often steeper. Recoveries are almost always lower than conventional. So everyone here, most of you are geologists, so you'll be very familiar with this, but when we're presenting this sort of stuff to bankers and financiers and people who are not, who don't understand our sciences, a lot of them think there's these giant pools of oil and gas underground, just giant open caverns that you tap into. Obviously that's not the case. Oil and gas is trapped in rocks in very tiny pore spaces. So it can be misleading for people who are not familiar with the industry that we call them oil pools and oil reservoirs. So this is just basically saying that volumetrics from a high level is taking a look at the total rock volume, figuring out how much space is in the pores of the rock, and then figuring how much of that space is occupied by hydrocarbons. That's exactly what this says. So you start with the rock volume, then you look at how much of that rock volume is taken up by hydrocarbons, and then you estimate a fraction of those hydrocarbons that are likely to be recovered. So 10 years ago, this was used, and by the age of this slide, they're probably talking about 15, 20 years ago now. It was a prime method in a lot of plays in Canada and the world. We're starting to use a lot more analogies, and that's really just a function of the data available. You start with volumetrics when you don't have a lot of data available to you, and then as soon as you have a lot of producing reservoirs with mature performance, you can start to use more accurate methods than volumetrics. That said, we still use volumetric calculations as verifications or cross-checking to make sure that our recoveries that we are defining based on analogs and performance are reasonable, because we also have a lot of data on total recovery factors in our mature basins. So the general equation, the petroleum in place is equal to area times the net pay times the porosity times the saturation of oil or gas or both, so the hydrocarbon saturation, and then it's adjusted by a formation volume factor, which we get into, but it basically reflects the change in volume as you change the pressure and temperature that the oil is subject to, or gas? No, it depends on, we'll talk a bit more about it later, but it depends on the type of oil, how light it is, how heavy it is, how much gas is inside it, and it's highly variable for gas. All right, so a little more in depth on the terms. So area, so when you're doing volumetrics on a single well, the area you're going to use is going to be your anticipated drainage area for the well. If you're doing volumetrics on a pool, it's going to be the total area of the pool. So you're really looking at the total drainage area associated with whatever asset you're trying to evaluate. Pay height, it talks about gross and net. So gross pay is the total height of, or the total thickness of the hydrocarbon bearing layer, and net pay is the thickness of the hydrocarbon response in that layer. So you might have an oil accumulation that has 30 meters of oil and 5 meters of water. The gross pay would be 35 meters, that's the size of the reservoir, and the net pay would be the 30 meters of oil. Porosity is the effective storage space, so it's the tiny pores within the rock that hold the oil and gas. Fluid saturation, so in almost every reservoir you're going to have an oil saturation, a gas saturation, and a water saturation. To simplify things, for oil reservoirs we lump the gas in with the oil and we just call it an oil saturation, and for gas reservoirs we kind of ignore oil. Formation volume factor, again it talks about as you bring oil to surface, the actual volume of the oil will shrink, because gas will evolve out of the oil, or the gas that's inside the oil will shrink. Gas, on the other hand, expands as you bring it to surface. The key data, so this is what you need in order to perform volumetric analysis. So you have to have penetrated the formation, you have to know what you're looking at, so you have to have well logs. It helps to have core, you don't necessarily need core data. But you need to understand the physical properties of the reservoir, and you need to have pressure and temperature information. In established basins like Alberta, we have pressure gradient and temperature gradient rules of thumb, but each subject reservoir, you can have overpressured and underpressured reservoirs, and temperature is pretty straightforward. The temperature of the earth it follows a fairly set gradient, but pressures can vary greatly. So when you hear about drilling rigs around the world having major issues with blowouts, that's because companies will do their best to estimate what pressure a reservoir might be under, but if they drill into that reservoir and it's significantly overpressured and they don't have the right density of drilling mud to keep the fluids down, that's when you start to see well blowouts. So rock volume, which is area times the net pay height, you'll see in evaluations, in a lot of evaluations, you'll see geologists that have included net pay maps or isopac maps, which show the contours of a pool, so they've mapped out the entire pool. On wells, instead of mapping things, we generally just assume a drainage for the well. Because we only have a single data point of net pay, we just assume that net pay is consistent enough to be applied to the drainage area for the well. Estimates, there are rules of thumb again in Alberta. If you're trying to estimate a single well pool, we have a list of formations or age equivalent formations and what the average size of one of those pools might be. So we have a whole bunch of guidelines in Alberta and Canada for what a reasonable approximation for a starting point could be. Major principle, you multiply the area by the net pay to get the rock volume. So the volumetric equation, there's two different ones. There's one for oil, one for gas. The major differences are really the constant and the formation volume factor. So I'm not going to spend too much time on this. The 7.758 is just to convert from metric to imperial. Here's the SI equivalent. So this is your metric equivalent. So area in this one is in acres, net pay is in feet, so H is in feet, and the ALTA, the recoverable oil in place that you'll get by using this calculation, is thousands of barrels of oil at the surface. In the metric equation, you can see the multiplier is different at the beginning. Areas in hectares, net pay in meters, and you get thousands of cubic meters at surface conditions. So going a little bit more into the formation volume factor. The volume of reservoir oil, oil will almost always, it will have some amount of gas in it. There's a, dead oil is, we call it dead oil and live oil. Dead oil is, there's very little gas in it, and your formation volume factor is going to be very close to 1. Live oil has a lot of oil and gas, so there's a range depending on how much gas is in your system for how much shrinkage or how much your oil volume is going to change when you bring it to surface. So we call shrinkage the inverse of the formation volume factor. So a couple slides back, if you look at the actual formulas, you'll see it's 1 over BO. So that term, 1 over formation volume factor, is referred to as shrinkage in the industry. How do we get this data? They will produce the oil. They'll take if gas evolves from the oil, they'll take a sample of both the oil and the gas, they'll take it to a lab, and they will repressurize it and increase the temperature to reservoir conditions. And then they will reverse the process and measure the difference in the volume and measure the various physical properties of the oil. So that's what happens if you have no data. Like I said, in Alberta we have a lot of data. So in Alberta we have guidelines and tables that you can basically look up your oil API or your gas composition, your GOR, and you'll have an approximation of the formation volume factor for that oil. So the opposite of oil, the reservoir volume of gas is going to be much lower than gas at standard conditions or gas at surface. As it comes out and the pressure and temperature drop, the gas expands. So the gas formation volume factor is a little bit more complex than oil. You need to know the pressure and the temperature because gas volume is dependent on pressure and temperature. So we have various sources of information for the gas volume in Canada. They require a little more calculation than the oil. The oil is usually lab testing or analogs. Gas is usually calculated. But we still do have published data for pools and their gas formation volume factor. So if you were to calculate gas formation volume factor, this is the inputs you require. So you need to know the reservoir pressure, pressure at standard conditions, that's known obviously. Then you need to know the reservoir temperature, which as I mentioned is fairly easy. So reservoir pressure can be challenging to obtain. You usually have to do a pressure test on the reservoir. Reservoir temperature, because of the thermal gradient of the earth, is fairly easy to calculate. Then you need the reference temperature at standard conditions, so that's either the 60 degrees Fahrenheit or the 15 degrees Celsius. And then the one that takes some calculation is the factor Z, which is the gas compressibility factor, or gas deviation factor, which is derived from the real gas law. Okay, so as I was saying, where do we get this data? Pressure and temperature, you either calculate it from test data, you get it from pools that are readily available in most of Canada but may not be in other jurisdictions in the world. We have a geological survey that talks about the gradients of pressure and temperature in Canada. Or you can look at offset wells. If another company has done pressure testing, eventually that comes into the public domain. So there's a couple of rules of thumb. Excuse me. There's a couple of rules of thumb down at the bottom. Pressure gradient is showing you per 100 feet what the standard pressure will be. Like I said, it's a good starting point, but actual reservoir pressure could be overpressured or underpressured depending on the conditions it was deposited in. Temperature gradient is fairly accurate at 1.5 degrees Fahrenheit per 100 feet. When you apply the temperature gradient, you have to adjust for surface temperature. So getting back into the compressibility or the deviation factor, it's required for gas volumetric calculations. It comes from the real gas law. It varies with gas composition, pressure, and temperature. So most petroleum softwares will have an automatic built-in module for calculating Z as long as you input the gas composition data or specific gravity of the gas. It's simply based off, it's directly based off formulas that don't change as long as the inputs are correctly applied. So the hard part of estimating the compressibility factor is finding what's called pseudo-critical pressure and temperature. So I'm not going to go into a lot of the theory as to why, but you require a couple of pressure and temperature inputs that are specific to the gas you're looking at. You have to correct for H2S and CO2 for sour content of the gas. There are a lot of correlations for figuring out what the critical pressure and temperature are for your gas. So again, it's just making you aware that these are the inputs that you kind of have to track down before you can do an accurate volumetric gas calculation. So you can see there's a lot of theoretical values that you have to come up with for your in-place gas. So once you have the original gas in place, so you've got a total volume of gas in the ground, to take that from an OGIP or total recoverable volume to a reserves volume, there's a couple of additional factors that need to be applied. So the first one's the recovery factor. You have to look at how much of the gas you think is reasonably expected to come out of the ground. And then you have to apply a surface loss or a shrinkage factor. So recovery factors, I actually think the next couple slides will go into more detail on these. But the recovery factor, pretty common term, I'm sure you're all aware of it. Surface loss describes the shrinkage or the gas losses taking it from reservoir and wellhead through to a sales point. So recovery factors, it's a fraction of hydrocarbon recovered. It varies even between wells in the same pool. It's very reservoir specific. It has a significant effect on the reserves calculation. And there's no simple correlation between recovery factor and other reservoir variables. So like I said, it's very dependent on the reservoir immediately around a well or asset. Generally speaking, recovery factors are low in low permeability. So when we get into unconventional reservoirs, we'll talk a bit more about ranges of recoveries, but in general, unconventional or tighter reservoirs are going to have lower recovery factors than conventional or higher porosity and permeability reservoirs. Recovery factors depend on drive mechanism, rock properties, fluid properties, production methods, recovery techniques, abandonment pressures, and economic factors. So there's a lot of issues that go into recovery factors. So when we're doing volumetric calculations, as evaluators, this is where we spend most of our time. You have to spend some time pulling together the data and getting the parameters for the rock volumes in the OGIP or OIP. But where evaluators will spend a lot of time is determining the correct recovery factor for a given reservoir or field. So again, specific to Canada, because we have relatively good disclosure, our energy regulator has actually calculated recovery factors on almost all of the oil and gas pools in Canada. The data, it varies significantly, the data quality, so you have to take the recovery factors they've calculated with a grain of salt because they've done it from a very high level. But they've documented all of the known pools in Alberta, and they've documented the reservoir properties of those pools, and they've calculated a rough in-place volume, and they apply a recovery factor based on analogs or other pools or cumulative production to date if they have a very mature asset. So primary recovery, we have the drive mechanism on the left side. So expansion drive is as you drop the pressure in a reservoir, you'll start to get gas evolving, and as that gas evolves and expands, it's going to push the oil towards your wellbore for more production. Solution gas, same thing as expansion gas. So expansion gas is talking about, the first three are all very similar drive mechanisms. They're all based on the principle that as you reduce pressure in a reservoir, the gas is going to expand and apply energy to the reservoir to produce the surface. Then you have edge water and bottom water. Again, very similar principles. That's aquifers around the reservoir that are always pushing against oil because it's more buoyant than water. And gravity. So there are certain accumulations where gravity will have a significant impact. If you look at the oil sands, there's when you're applying a technology like steam-assisted gravity drainage, you're using the buoyancy of oil and gravity effects to produce the bitumen bar. Recovery ranges 2 to 5%. So expansion, if you have a relatively small amount of gas in the reservoir, which is where this expansion drive comes from, you have a hard time. There's not a lot of energy. Gas is really the energy in a reservoir. So if you just had a pure oil reservoir with very little gas, there's not a lot pushing the oil or helping the oil get to surface. So recovery factors are relatively low. As soon as you get more gas, as soon as you see solution gas, gas cap, you're starting to see a lot more energy in the reservoir. It's a lot easier to produce larger portions of the oil in that reservoir. So you see the recovery range start to increase. Edge water and bottom water effectively works as a pseudo water flood, and as long as you operate the wells properly, it can really help your recovery factors by sweeping the oil towards the production wells. And gravity drainage is a very efficient process. All right, Alberta pools. Most Alberta oil pools are solution gas drive. What we see in Alberta, the general guidelines on the previous table are a bit higher than what we see in Alberta. 0 to 15%, very rarely over 20%. This is talking about oil pools. Use 48%, so these are general guidelines for Alberta, but they just show you how much of the oil and or gas is left in place, especially on the oil side. This is really talking about oil, but a lot of Alberta's oil and gas pools are sitting at single-digit or very low double-digit recovery factors. So in Canada, even though we have very mature oil and gas assets with much of the ultimate recovery that's available with current technologies already recovered, there's still 80 to 90% of the oil left in the ground in a lot of Alberta and Canada's oil pools. The problem is finding a technology that allows you to commercially produce the remainder. It talks a little bit about pumping and gas lift. So you can apply artificial energy to the reservoir by adding pumps either at the bottom of the wellbore or the top of the wellbore to increase the pressure differential between reservoir and surface. So enhanced oil recovery, again, because Canada and Alberta is a relatively mature basin, we have a lot of EOR projects, which is really trying to get at that remaining 80 or 90% after primary production. So some rough rules of thumb: implementing a water flood usually doubles primary original recovery factors. So if we were looking at primary recovery factors in the 4 to 8%, this is telling you that if you implement a water flood, a reasonable rule of thumb is that you're going to get 8 to 16% total recovery by the end of your water flood. There are more efficient processes and better, basically polymer and CO2 flooding improves your recovery, it improves your sweep efficiency in the water flooding process or the gas flooding process. So you make, this is saying rule of thumb, you may triple your original, so you might get another 4 to 8% out of the reservoir. The caveat to these higher recoveries is higher costs. So as you move down this road, as you go from primary production, which is relatively low cost, you move into water flooding, you're adding incremental cost, and then when you're getting into chemical flooding, CO2 flooding, you're getting into much higher costs. So those incremental barrels have lower netbacks. So you made the most money on the primary production. You make smaller margins on your secondary production, and you make even smaller margins on your tertiary production. So again, giving you a little bit of background on Alberta, we talked about the hundreds of thousands of wells in Alberta. There's about 14,000 known pools. The mean recovery factor of those pools, so the average recovery factor is 17%, so that's including primary, secondary, and tertiary processes across the province. Median is 10%, and the mode, so the most common recovery factor in Alberta's pools is 10% if you exclude all of the tiny single well pools in Alberta, or 1% if you include all of the pools in Alberta. So you can see the most common recoveries are very low, but on average, we're in a relatively mature, sort of 10 to 20% range of recovery is relatively mature in the oil and gas world. So moving into gas. Gas is a very different story. It's a much more efficient recovery process because, as we were talking about earlier, gas is really what provides the energy in a lot of reservoirs. So if you have a pure gas reservoir, your recoveries can be very, very high. Gas expansion drive, 70 to 95% recovery factor. So you're getting virtually all of the gas out of the ground. Water influx drive, 40 to 60%. So this is saying that you either have gas on top of water or you have water encroaching from the sides of a gas reservoir. And the reason the recovery is lower is because at some point that water starts being produced preferentially from the gas, and as soon as a well is watered out, there's a few things you can do, but when you're fighting water production, you're pretty much at the end of life of your gas pool. So again, this 40 to 60% is saying it depends on the strength of the water drive. So if you have a stronger water drive, it's easier to cone water into your wells earlier. It's easier for your production to be impacted by the water earlier in the production life. So you'll have lower recovery factors ultimately. So now moving into the unconventional world to give you an idea. So we were at 70 to 95% for most conventional gas. If you start getting into Musqueam, Montney, so shale gas, very tight gas. So Musqueam shale is some of the tightest gas. That's true shale gas in British Columbia and Canada. Estimated recovery factor of 20%. So you can see it's an order of magnitude lower than conventional gas. Montney hybrid shale. So Montney is the permeability in Montney is about an order of magnitude higher than the Musqueam, so it's not nearly as tight. 30 to 50% is a typical range. I would say that's more like 20 to 60% now that we're seeing a little more data. Sweet spots have high recovery factors, so one of the things you have to be aware of when you're applying recovery factors from analogs is that companies will always be as efficient as possible with their capital, so they're going to drill up the best areas of a reservoir first. And so if you're looking at a fairway and you're looking at a recovery factor in a fairway and you're trying to apply that same recovery factor to fringe wells, you have to adjust it because as you move into poorer reservoir, your recovery factor is going to drop. Okay, so recovery factors. I'm not going to spend a lot of time on the next several slides. This is starting to talk about the relationship between abandonment pressures, how you determine ultimate recovery from a more theoretical basis. So this is saying your recovery factor for a gas pool. Gas pools are the simple example, which is why we have these calculations. It's proportional to your initial reservoir pressure, your initial compressibility factor, and your abandonment reservoir pressure and your abandonment reservoir compressibility. So gas has a very simple relationship with pressure in terms of recovery. And what this is saying is, so the abandonment pressure You have to know what your abandonment pressure is going to be, and there's a lot of factors that go into abandonment pressure. That's where your economic cutoffs, your reservoir deliverability, the margin, the production rate of your well all impact the abandonment pressure. So if you can understand your abandonment pressure for a gas reservoir, you can make a very accurate calculation of your ultimate reserves. Getting into estimating abandonment pressure, so because there's so many gas pools in Alberta and we have so many data points, this is a simple rule of thumb for what an abandonment pressure might be for a given reservoir. It's just based on reservoir depth. So it's a very simple high-level correlation, so it's a good first stab at what might be an appropriate abandonment pressure to use. Getting into an example of an 8,000 foot deep well, saying an appropriate abandonment pressure might be in the order of 300 psi. So getting into some specific examples for volumetrics. So the Viking play in Alberta and Saskatchewan is a relatively, it started out with what you can see here is vertical producers. So it started out, it's got a couple layers to it. There's an upper layer of the Viking that is relatively porous, relatively permeable, that they produced using conventional means, but it was never very prolific. It was low rate wells, low rate vertical wells, so they drilled a lot of them. Recently they've been going back into them with horizontal multi-stage fracking and getting much better results out of it because there's a lower level of the reservoir that's also oil bearing, but that's much tighter. So this is showing you a net pay map that some geologist has done. So you can see all the dots are wells that have been drilled, they've been logged. The geologist has taken the net pay from those wells and then he's contoured the net pay for this specific pool. So this is saying they're drilling these on very high density because the recoveries there's not a lot of energy in this reservoir, so the recoveries are very low and you have to drill very tight spacing wells. So a section is 640 acres to give you a concept of size. It's giving you some average parameters, 28% porosity, so that's fairly good porosity. Water saturation of 25%, so that's saying 75% of your pore space is hydrocarbon. You can see the shrinkage factor is 0.9, so we talked, someone was saying around 1 for some of the stuff the Chinese are using. Recovery factor says 48%, so you have to choose which. This is an exercise. You're going to see a bunch of stuff in this afternoon, especially. There's a bunch of exercises that I'm just going to walk through, but normally it would be more interactive. This is just filling in the parameters. So the net pay, they're saying on average is 20 feet or 6 meters. So this is walking through, these are all the inputs that we were talking about for original oil in place, for volumetric calculations. So this is from that net pay map, and from what we know from the well logs, this is all the geological data that's required to calculate. You start with bulk volume. Bulk volume is rock volume, so that's just area times net pay. Then you multiply by your porosity, so 28% of your rock volume is open space. That's what porosity is telling you. And then you multiply by 1 minus your water saturation, so you multiply by your hydrocarbon saturation. So if this is telling you from the well logs that you're estimating that 25% of the fluid in the pores is water, so you're estimating that 75% of the fluid in the pores is oil or gas, in this case oil. That's how they're getting the oil saturation. Then they apply the oil shrinkage factor, and they multiply it all through along with the constant you saw in that previous slide. And if you actually did the calculations and you did the math, you would end up with an OIP of roughly 2 million barrels. So what's the estimate? Roughly 2 million barrels. If you expect the recovery to vary between 4 and 8, it's talking about how do you achieve that recovery, how do you get a 48% recovery. And it's saying you have to drill high density. You have to drill 8 wells in that drainage area to get within this 4 to 8% recovery range. So that was an oil example, volumetrics. This one's gas, so this is Montney, so it's not as tight as shale gas, but it's a very tight unconventional gas. Very different type of reservoir. So net pay, 26 meters, average porosity, 7%, so you can see on the last example, the Viking, we had a porosity of 30%. So 30% of the rock was open space. In the Montney, only 7% of the rock. So it's much tighter and there's much less pore space. SW is a little bit lower at 20%. It gives you the initial reservoir pressure, gives you the initial reservoir temperature, or the reservoir temperature, and they've given you the compressibility factor. So they've gone to the tables, they know the composition of the gas, and they've given you an approximation of. So why they chose the Montney, they want to talk about fractures a little bit, calculate the OGIP, and check the reasonableness of the recovery factor. So reiterating your OGIP calculation parameters, and then just outlining everything, all the parameters that they're estimating for this example. I guess specific to this, one of the big unknowns in these very tight gas plays, especially the ones that are being produced using hydraulic fracturing technology, it's very hard to estimate how wide your fracture network is, how much of the reservoir you're actually accessing. So one of the big questions in North America right now is, what is the area of drainage for a well? How much reservoir is a well actually accessing? So this is talking about that issue right now. It's saying, how big is the fracture envelope? How much drainage are you accessing with a single well? So it's saying with 4 wells per section, so 4 wells in a 640 acre spacing. Your well spacing, so you have 400 meters in between your wells. That's the distance, your interwell distance. When you're drilling horizontal wells, they're generally in the 1,600 to 2,000 meter long, so they're 1.5 to 2 kilometers long. And the height in these Montney formations, the Montney can be a very, very thick formation. So it could be 200, 300 meters of Montney shale. When we're looking at, so it gets subdivided into certain layers, and then what it's saying, 75 meters, it's saying we don't think you can propagate a fracture more than a certain height. And that's based on a lot of data we've seen to date. So 50 meters to 75 meters is sort of the maximum distance we've seen fracs propagating. So we kind of bracket the size of our drainage area based on what we know from fractures. So again, filling in parameters based on the last 2 slides, and ultimately arriving at a hydrocarbon pore volume. So now they're calculating the gas formation volume factor, or the gas shrinkage. So the inputs that are required, initial reservoir pressure, the reservoir temperature, the compressibility or deviation factor, and then you need standard pressure and temperature for the correction. Plug all that into the formula, and you have a gas shrinkage. Okay, so to calculate the OGIP, you take the hydrocarbon pore volume, which is the amount of rock that's filled with gas. You multiply it by your shrinkage, and basically what they're saying is the OGIP for the drainage area that they've selected is 11 BCF. It says 11,000 million cubic feet, so it's 11 billion cubic feet. Okay, so now it's talking about, so now you have an OGIP estimate. Now it's talking about applying a performance technique instead of applying a recovery factor. So in the Montney, we generally, some evaluators, there are some evaluation firms that will take that OGIP, apply a recovery factor that's applicable for the Montney, and back allocate that number to the number of wells in a drainage area. That's not the general approach that we take. We usually start with the well performance. We have a lot of Montney wells in Alberta, so we start with the average performance of a Montney well, and then we determine how many of those Montney wells will fit within the drainage area we're evaluating. And so we start in a lot of the Montney evaluations, we start with a recoverable volume based on performance methods. We'll be talking more about performance methods later, but we generally start with a recoverable volume in the Montney. Then we calculate the OGIP. Then we back calculate a recovery factor to make sure it falls in line with reasonable recovery factors that we've seen in the Montney. So this is talking about the performance of a well. It's saying the average well, the average 1 month to 2 month initial production of a well in this area is a little shy of 4 million cubic feet per day. This is saying the company is using a reserves life index. So we'll talk about a reserves life index when we get into the performance techniques. But a reserves life index is taking the producing rate of your well and the ultimate reserves attributable to that well and dividing the two. So you're going to take the ultimate reserve, say you have a BCF remaining of gas and your current production rate is 1 million a day. Your RLI is how many days it will take you at that rate to recover the gas. So the company is saying we're going to use an RLI of 3 years. An RLI is another approximation you can use for estimating ultimate reserves as a very rough calculation. So they're saying an RLI of 3 years is reasonable for Montney. So in order to determine what the recoverable gas volume is for the Montney well, they'll take the RLI of 3 years and they'll multiply this initial gas rate by 3 years. So 3 times 365 days times 3.8 million a day, and that will be their high-level estimate of the recoverable volume for that well. So that's exactly what this is doing. It's saying your recoverable gas in place is your 3-year RLI times your 1 to 2 month IP of 3.8 million a day times 365 days to convert your RLI years to days. And so they're saying 4.2 BCF, 4,161 million cubic feet is their rough estimate of what they think they can recover from the well. Then they're taking that 4,161, dividing it by so they're taking their 4 BCF, dividing it by their 11 BCF and saying the recovery factor they're estimating for that well's drainage area is almost 40%. We know from when we looked at the Montney recovery factors, we know that 30 to 50 or 20 to 60% is a reasonable range for Montney. So what this is telling you is they're asking, is there potential for more wells? Could we downspace? Could we put more wells into this same drainage area? And because you know that the recovery factor is already encroaching on 40%, this is telling you that no, you will have significant interference effects if you try to put more wells into the same drainage area. It talks, the next couple slides are going into recoveries of natural gas liquids. So this is when you have your rich gas stream coming out of the reservoir and you put it through a processing facility. So you can see there's 2 types of plants. We call them shallow cut and deep cut for how much byproduct they remove. So a shallow cut leaves a bunch of the natural gas liquids in the gas stream. A deep cut removes virtually all of the high value gas byproducts. So you can see that on the recovery percentages. So both the shallow cut and deep cut remove virtually all of the C5 plus, which, as I was telling you guys earlier, in Alberta, in Canada, C5 plus is the high value product, so that's what producers are mostly concerned with in Alberta, which is why a lot of producers are okay with shallow cut plants. They're less worried about C2, C3, C4. They're very concerned with getting as much C5 plus out of their gas as possible. But the difference in capital intensity requirements and the difference in operating costs between these 2 plants is significant. So shallow cut plants are much cheaper to build and they're much cheaper to operate. So the processing fees that the companies are going to be subject to in shallow gas are much lower than in a deep cut plant. A deep cut plant is more upfront capital, and it's also more operating cost. This is talking about how you calculate NGL reserves. It's giving you, there we go. It's giving you the recovery constants. If you were to recover 100% of the NGLs, what would it be? It's applying an efficiency to those recovery constants, and it's giving you your shallow cut and deep cut yields. So these are called natural gas liquids yields, and they're a representation of how much C2, C3, C4, and C5 plus you're going to remove from your gas stream, and they're expressed in barrels per million cubic feet of gas. Okay, to talk about surface loss in gas, not all of the gas that comes out at the wellhead is marketed. It's not all sold. We talked about shrinkage. Some gas is lost to sweetening, so that's removing H2S and CO2. Liquids recovery, when you refrigerate the gas and remove NGLs, it reduces the volume of your gas because you're removing those ends. Processing fuel, this is everything from generating electricity for compressors and pumps, or feeding natural gas as fuel for various processes in the field. And other losses, there's certainly shrinkage. It could be flaring losses, it could be a number of things. All of this combined is termed surface loss or shrinkage on the gas. So what comes out of the gas? Nitrogen, it pretty much sticks around. You don't want high nitrogen content in your gas because it doesn't help your heating value at all. There's no value to it, but it just kind of sits there. CO2 and H2S, there's a minimum threshold. You can have a minimum amount of CO2 in your gas. H2S has to be completely removed. So whatever percentage your gas composition is CO2 and H2S basically comes right off the top of your gas. So if your raw gas at the wellhead is 1% CO2 and 8% H2S, you're going to have a 9% shrinkage right off the bat. Methane, trace amounts lost in processing, most of it is fuel. So this is natural gas that's used for fuel. You do lose a little bit as it goes through the plant. Ethane, it depends on whether you're going deep cut. If you go with a deep cut plant, you will have some losses due to ethane. If it's shallow cut, they leave all the ethane in the gas stream. And C3 plus depends again on the efficiencies of your plant. And helium is the same as nitrogen. It's just kind of there. So surface loss, how do we calculate it? The best way to calculate it is reviewing the operating statements. So as we've visited in Alberta, we have very good data on raw gas production. It's all publicly reported. We know what comes out of the wellhead. And then evaluations companies are required to provide us with their lease operating statements, which detail their sales gas volumes. So we have the raw gas volumes in the public domain, and we have the sales gas volumes reported by the company in their lease operating statements. So that's how we generate, that's the way we like to calculate surface losses, is we simply compare sales volumes to the raw gas volumes that were reported at the wellhead. If we can't do that, we'll do theoretical calculations based on the processes used. So we'll usually assume some small amount of surface loss, some amount of fuel losses in the order of 0 to 5%, well it's usually 1 to 5%. And then we will look at the gas composition and what type of facility it's running through, and we'll do a theoretical calculation on how much gas will be lost when they remove the NGLs. So rules of thumb: minimum surface loss 5%, unless you get very large. Some very large plays will have lower surface losses in the 3 to 4% if you have a lot of gas, just because the absolute amount of gas that gets lost is relatively the same, but because you have so much, basically your fuel gas losses, etc., are just a smaller percentage of your total gas loss. But 5% is generally a good rule of thumb. If you see surface losses or shrinkages less than 5%, there should probably be an explanation on it. And another rule of thumb: for every 8 barrels per million cubic feet of gas that you have is an NGL yield. So NGL yields in the Montney range from 10 barrels a million to 60 or 70 barrels a million. And for every for every 8 barrels per million of NGLs, you can add essentially you can roughly add 1% of shrinkage. So again, going back to the Montney well that they were talking about, they're just going to compare the first Montney well and the second Montney well. So total recoverable gas volume. So the first Montney well was the one that was drier. It had no H2S. It was lean. So the surface loss they're saying is going to be basically fuel gas losses, 5%. The second Montney well had higher NGL yields. It would have more processing shrinkage, and you can see they've estimated a 12% surface loss. So you can see we've gone from recoverable raw gas. This is what we assumed would come out of the wellhead to your gas reserves after we've applied the shrinkages or the surface loss. So the gas reserves are what will actually be sold at a reference point. And the NGLs, so you can see we've gone from a pure gas stream that includes all the NGLs at the wellhead to gas reserves and NGL reserves. These NGLs would also be reported as reserves as sales volumes. So summary of volumetrics. For reserve calculation, we need to estimate drainage area, net pay, porosity, water saturation or hydrocarbon saturation, they're generally the same thing. Formation volume factor, shrinkage, recovery factor, and surface loss of process shrinkage. And again, from an evaluation standpoint, recovery factor is where we spend most of our time trying to figure out what's appropriate.